Hello, welcome to the second day of CoNGA 2022, Conference on Next Generation Arithmetic. I'm your General Chair, John Gustafson, and our first speaker is going to be Peter Lindstrom from Lawrence Livermore National Laboratory. Before I introduce him, I want to remind people to use the Pigeonhole feature. I think that we're going to get the QR code that you can scan it in. There it is. And please feel free to submit all questions and comments that you have. I think we'll take them at the end, but do give us lots of feedback and then react with Peter's talk if possible. Peter Lindstrom is a computer scientist at the Center for Applied Scientific Computing at Lawrence Livermore. His research focuses on data compression, number representations, and scientific visualization. He is the chief architect of the FP-ZIP and ZFP floating point compressors and leads several ongoing research projects, including the ZFP effort as part of the US DOE Exascale Computing Project. He is a member of he's one of the hardest working members of the Posit working group developing the standard for Posit Arithmetic, which has recently come to fruition. And this is his third presentation at CoNGA, I believe. He's presented every year, and almost every year, people tell me that was the best paper of the whole conference. So let's see if he can hit it out of the park again. Go ahead, Peter.
Now, John, can you hear me?
Yes.
Okay, excellent. Well, thanks for the very nice introduction. So I'm really excited to be here to talk today at CoNGA. It's been a few years, but I'm really glad that John got this going again. I actually had some work that I did a few years ago that I didn't really know what to do with, but this was sort of the perfect opportunity to put together a paper on this. So what I'm going to be talking today about is sort of a generalization of posits and other universal codes from scalars to vectors and tensors and essentially higher dimensional quantities. So what's really motivating some of this work, let's see if I can get to the next slide here. Click. There we go. As you know, these huge quantities of floating point data that get generated in scientific simulations, observations, and experiments. And in many of these cases, we're talking about terabytes per day. And there are really two use cases for this. So one is just for the sort of archival storage of the data, potentially for later analysis, as well as communication of this data that might be across the internet, but it might also be between compute nodes while, for instance, the simulation is running. The other obvious use case that's probably more pertinent to CoNGA is using these new number representations for in-memory storage and for arithmetic. So I'm going to be touching on both of these use cases a little bit later on in the talk. But I do want to point out that some of the fundamental assumptions that we're making here is that the data lives on a multidimensional Cartesian grid, which is often the case, and that the data varies somewhat smoothly. And that tends to be the case when we want to represent, for instance, physical fields like temperature or pressure in many of these simulations. So to sort of give you an idea of why this might be important, what I'm showing here on the top left is a three-dimensional velocity field from a turbulent mixing simulation. And I've taken a two-dimensional slice of that over here. And I've then represented this two-dimensional slice of real numbers using 16-bit posits. So what you're seeing on the bottom here are the 16 different bit planes of this posit representation, starting from the most significant bits in the top left corner here, and we go into less and less significant bits until we get to the least significant bits, where essentially the bits look like they're, for all intents, random, right? But if you look at the leading bits of the posit representation, you can tell that the first three bit planes, for instance, are all identical. The fourth bit plane is essentially the same as the previous three bit planes, but it's kind of sort of inverted. But what you're seeing here is that there's a lot of potentially redundant information here that we're not exploiting. So two observations to make here. First is that consecutive bit planes are often correlated, as we can see here. And that's essentially due to the low dynamic range of the data. So even though in many computations, we might need a lot of dynamic range to avoid over and underflow, the actual quantities that get represented, for instance, each field and each iteration of a PDE solver tend to have a much lower dynamic range. The other observation is that adjacent grid points are often correlated. So if you're a black pixel in one of these images, you're very likely that the neighbors are also black, and vice versa for white pixels. So there's some redundancy here that's not being exploited in the standard Posit implementation or Posit representation. So this wastes storage, which in turn sacrifices accuracy in terms of accuracy per bit stored. So we want to get around that, and that's really what this talk and the paper I wrote is about. All right, so to set the stage, I'm going to be talking first. I'm going to give a pretty extensive background on posits as well as ZFP, which I'll get to a little bit later, for those of you who are not familiar with that. But let's just talk about posits first. So sort of the traditional perspective on posits is that it's a representation that partitions a binary, say 16 bits of a binary into a sign bit, a regime field, an exponent field, and a fraction field. And then you can represent essentially any non-zero number using a combination of those fields, like so, like in this equation I've shown up there. A couple of years ago, well, I guess about 4 years ago, we presented a paper at CoNGA 2018 where we looked at this in a slightly different way, where we essentially consolidated the regime and exponent bits into a single variable length code that encodes the base 2 exponent of the number. And as it turns out, that's essentially a generalization of Golem-Rice codes to sign quantities. Yet another interpretation of this is that that I presented at well, I had a paper at Arith 20 that didn't get presented, unfortunately, because of COVID. The idea is that posits using an exponent size of 2, which is in the current Posit standard that we'll hear more about later today, is essentially a hexadecimal representation of numbers, where the regime bits, in essence, tell you how many significant hexadecimal digits there are. For the leading non-zero hexadecimal digit, we use a variable length Huffman code that's based on the Benford's law that gives you essentially a probability distribution of the different digits in the leading hex digits. And the remaining digits are essentially just raw hexadecimal digits. So that's a very different perspective from the previous representations. At CoNGA 2019, I gave yet a fourth interpretation of posits, where the idea is to cast this as a process of bisecting intervals, not necessarily at the midpoints, but splitting intervals in half. And in order to encode a posit or any universal number, the idea is that we need two different functions. We need a generator function that produces a monotonic sequence of real numbers, where you essentially just apply this generator function to the previous value in the sequence to get the next one, and you keep going. So for instance, for posits in the current standard, we simply just multiply the previous number by 16 and keep doing that until we have bracketed the number between two finite numbers. Then we proceed from there to use a refinement function where we essentially just compute some version of a mean between the two endpoints of the interval. That might be the arithmetic or the geometric mean in the case of posits, for instance. But in either case, for both of these functions, we're making binary comparisons against some number to see if the number that we're trying to encode is below or above that split point. And that's how we produce, that's how we encode posits in a very simple way. And we will see later how we can reuse this concept to encode multidimensional real numbers. All right, so in terms of this generator function that I just spoke of, I've listed here in this table a few different generator functions for different number systems. So you can specify an entire number system just by specifying this generator function as well as a refinement function. As you can see, for some of these well-known or previously known number systems, they have very simple generator functions. So in the case of posits, for instance, we just multiply by a base b, and the base here is dependent on the number of exponent bits in posit terminology. I said there's also a refinement operator that takes the two endpoints of the interval for posits. We typically compute the arithmetic mean as long as the two values do not differ by more than a factor of 2. If they do, then what we do is that we take the base 2 logarithm of two numbers, and then we recursively invoke this function. So if you do this for posits, you'll see that this actually turns out to be the geometric mean in case B and A differ by more than a factor of 2. All right, so let's return to this issue of correlation and redundancy in the representation. So one way to combat this is by performing what's called decorrelation. And in order to do so, we first need to look at how values are correlated. So what I'm showing here is a very simple two-dimensional matrix that I've partitioned into small blocks of 2 by 2 values. And then what we're going to do is we're going to treat each location in these blocks as a random variable. So we have 4 different random variables, x, y, z, and w, that correspond to, say, the upper left for x, upper right for y, and so on. And we're going to look at how these random variables are correlated. So using decorrelation, we just apply a linear transformation to the data that transforms it into a new basis in which it is sparse. There are a large number of different decorrelating transforms that have been proposed in the past. Probably the most famous one is the discrete cosine transform that's used in JPEG image compression, for instance, but there's a slew of other ones. If you want to do this in an optimal fashion, then you want to perform decorrelation so that the resulting random variables after this transformation are entirely decorrelated. In other words, when you look at the covariance matrix, it becomes entirely diagonal. So if we're starting from a covariance matrix that has, say, unit variance on the diagonal, and everywhere else has this is just the Pearson correlation coefficient that's between -1 and 1. So for this case of 2 separate random variables, we decorrelated by finding the eigenbasis of the covariance matrix. And in this case, that eigenbasis is actually independent of rho. It turns out that that basis is given by this matrix Q that's slightly scaled in this particular case. But when you apply that, you decorrelate it, and you end up with a covariance matrix that's perfectly diagonal, meaning that the variables at this point after decorrelation are entirely independent. In a more graphical depiction of this, what we're doing is, what I'm showing here is the joint probability density function between 2 correlated variables, x and y. And you can see that they correlated because as you increase x, you also increase y. So you're seeing these contours of the probability density function here. What I've also shown is this lattice here of points that actually represent the values in say, a posit representation, say a 3-bit posit representation for this particular, that essentially optimal for this density. But the problem here is that you still have this correlation that you want to get rid of. So when you perform the correlation, in this particular case, what you end up doing is essentially just performing a 45-degree rotation of the original function. And when we do so, we realize that there's a much larger variance in the transformed x direction than there is in the transformed y direction. So we can exploit that by using, say, more precision along the x-axis than we use along the y-axis. And as a result of doing that, we get sort of a tighter grid spacing of this, and we also get sort of a better fit of the available representative values in terms of being a good fit to the probability density, and that's really something we want. If you do this for a two-dimensional domain, where in this case I've partitioned the domain into blocks of 4x4 values, and then I've computed the distribution for each position within these 4x4 blocks, and then plotted that distribution as a box plot. So what you're seeing here is the first, second, and third quartiles of that distribution. So they're just a standard box plot. And you're seeing that for each of these 16 different values or random variables within the block, they essentially have the same distribution. Okay. Now, after we perform decorrelation, the story is entirely different. So in this case, we use a decorrelating basis that is composed of the grand polynomials that essentially, modulo some technical details, are just simple polynomials that start with a constant polynomial. We then have the two linear polynomials in 2 dimensions. We then have the 3 quadratic polynomials and so forth. And if you look at the actual distributions here, you'll see that the one corresponding to the constant polynomial has a very tight distribution that's close to sort of maximum, close to 1 in this case. And what you're seeing here are these distributions plotted on a logarithmic scale. So what you can see is that for the remaining 15 coefficients, they are not only much smaller in magnitude, but you sort of have this monotonic decrease. So what you're seeing in the middle here is the median that's being plotted. And you can see that as we go to a higher total polynomial degree, you'll also see that the actual coefficient values are much smaller in magnitude, and in fact also have a much smaller variance that doesn't really show up well in this on this log scale. But at any rate, the point is that most of these coefficients have to be very, very small, and that's good for compression or coding. So the other point I want to make is that in addition to the correlation, it's a good idea to partition the domain into these small blocks for this reason. And that is that typically in a posit representation, as we saw earlier, we have to represent essentially the same exponent over and over, and that requires a lot of bits. So one way around this is to use what's called a block floating point representation, where there's only a single common exponent stored within the block. There are certain variations on this. For example, in NVIDIA CUDA, they store, instead of a common exponent, they just store the maximum floating point value, and then 16-bit fixed point significance that are scaled by this common floating point value that's stored in using 32 bits. Intel FlexPoint actually stores the common exponent and then n-bit fixed point significance. In JPEG image compression, again, we partition things into 8x8 pixel blocks, use the discrete cosine transform for decorrelation, and quantize coefficients and use Huffman coding. And what I really want to talk about next is ZFP, which is sort of, think of it as a JPEG for scientific data, for floating point data, that I published back in 2014, and that has really taken off in the scientific field. So the idea is to partition d-dimensional arrays into blocks of 4 to the d values, so say 4 by 4 by 4 values in 3 dimensions. We use a different decorrelating transform based on orthogonal grand polynomials, and then we use what's called embedded coding, and I'll return to that a little bit later in this talk. But the point here is that we can use a single exponent that gets amortized over many values within a larger block, so that we don't have to waste storage on essentially redundant exponent bits. And then also, by using the correlation, most of these coefficients are very small, have many leading zeros that can be compressed and represented very efficiently. So I'm going to go over the ZFP encoder in some detail here. This is sort of a high-level view. We start with a raw floating point array that's partitioned into these small blocks. We apply this block floating point transform that computes the largest exponent within the block and then aligns all the values within that block. And after this, the resulting set of values can be represented in integer form. So we can perform all computations in using integer arithmetic from this point on. Again, we perform this orthogonal or near orthogonal block transform. That's very efficient. We'll see that later. It's sort of a variation on the discrete cosine transform that's used in JPEG image compression, but it's more effective at decorrelating values that arise in scientific computations. The final stage is an embedded coding stage where we encode each bit plane from most to least significant bit at a time. And we can interrupt this process at any point, for instance, when a bit budget has been reached or when we reached an error tolerance, for instance. And the output of this is a compressed bit stream. All right, so let's dive into this in a little more detail. So ZFP uses this block floating point representation. So if we just look at standard IEEE floating points, if we look at a block of, say, 4 values in one dimension, then we represent that as as 4 independent 8-bit exponents. We have 4 independent 23-bit mantisses. We have some implicit bits and some sign bits. So in block floating points, again, we just compute the largest exponent within the block, and that's the only one that gets stored, and then everything else gets aligned to that. As a result, we have to reintroduce the implicit bits. We also have to pad with zeros on the left here when necessary. We also have to pad on the right with zeros to fit these coefficients into 32-bit integers. As you can see, if there's a large dynamic range within this block, then we might actually lose some of the least significant bits of some of these values. That tends not to really be an issue if you were to actually do computations between these values. For instance, computing the sum or difference between them using conventional floating point, then you would lose those bits anyway, so it's not really much of an issue. All right, the next step is to apply this decorrelating transform that's essentially run along each axis of the domain. In this case, it's a 4x4 matrix that has a bunch of C and S terms that correspond to sines and cosines of a single free parameter t. So no matter what choice of t, this matrix is going to be orthogonal. Now, a good question is, well, what's a good choice of t here? Does it really matter? So what we did was we threw a bunch of scientific data at this and varied t to see how that would affect the correlation efficiency as well as the coding gain. And those are 2 common metrics used for evaluating the efficiency of a decorrelating transform. And quite naturally, we chose the one value of t that gave us sort of the highest coding gain and correlation efficiency. And in some ways, that also turned out to be sort of a fluke because that particular choice of t results in a transform that can be implemented extremely efficiently just using additions, subtractions, and divisions by 2 that are efficiently implemented in terms of simple bit shifts. So you can see the actual code for implementing this matrix vector multiplication here. The final step, as I mentioned, is an embedded coding step where we encode bit planes one at a time. What I'm showing here are 16 coefficients where I've indicated a leading 1 bit for each coefficient. So everything to the left of these are just 0 bits. So what we're going to do here is that we're going to start from the most significant bit and we're going to apply what's called a group test. So in a group test, you test not a single bit, but many bits together. So when they are very likely to all be 0, you can indicate that just by emitting a single bit that indicates that. So if we're starting on the left here, we're testing the most significant bit plane. In this case, all bits within the bit plane are 0. So all we have to do is emit a single 0 bit to indicate that, and then we're done with that bit plane. So that gives us very good compression here. We move on to the next bit plane, and we realize that there's at least one non-zero bit within this bit plane. So to indicate that, I'm going to draw this little horizontal bar that indicates that we output at 1 bit for this group test. And then we need to figure out, where are these 1 bits? Maybe there's just one of them. So what we're going to do is we're going to actually start from top to bottom here and see if we can find a 1 bit. And we actually were lucky. We immediately found a 1 bit. And hopefully that was the only one. If it was, we can perform another group test. So we do that. And that group test also showed us that all the bits were 0. So we're done with this bit plane. And we essentially keep going with this and perform these group tests where many of the bits are 0 and get encoded very efficiently just using a single 0 bit. Here we are again. We encounter another leading 1 bit for the second coefficient here. And we similarly perform group tests, and we're done with that bit plane. Here's a slightly more interesting case where we've indicated, or we perform a group test here. We see that there's at least one non-zero bit, and then we march from top to bottom here. It's going to take us a while before we actually get to the 1 bit. There it is. Then once we find it, we see if that was the last 1 bit. Excuse me. And we can keep going until we encode everything here. But we can terminate this process at any point and get a valid approximation to the data. Okay. So that's it for how ZFP actually works. ZFP also comes with a set of C++ classes that implement multidimensional arrays that does this sort of block partitioning under the hood and allows you to have read and write random access to compressed data at block granularity. So ZFP handles all the details of how compression, decompression, and caching actually happen. The main difference between ZFP arrays and conventional arrays is that the user specifies the exact memory footprint they want down to the single bit if they need to, or they can specify an error tolerance also if they prefer that. So ZFP uses a conventional array API and by using C++ operator overloading. So essentially most of what you have to do to change your code from using conventional C or C++ arrays or SDL vectors is that you just change the array declaration and also specify, for instance, the number of bits per value of precision that you want. So this is how this might work in actual piece of code. This is a small diffusion kernel. What I'm showing here, or what I've done, is highlight the lines of code on the left that would have to be changed to work with ZFP arrays. Actually, not all of those lines have to be changed. Only the ones in orange here are changed. So in this case, we're declaring a 2-dimensional array that's nx by ny elements, and we specify the number of bits per value. I've also highlighted the lines in blue here. So ZFP provides multidimensional indexing that makes the code a little bit easier to read, but those changes are optional. So typically all you have to do are just change your array declarations and everything works just fine. All right, so the way that the application views this is that it interacts with this, in this case, 2-dimensional virtual array that's partitioned into blocks. On the far right here, these blocks are stored in compressed form somewhere in memory, but in between this virtual array and the compressed blocks, ZFP maintains a software cache of decompressed blocks so that you don't have to decompress a whole block each time you access an array element, or conversely, compress a whole block once it's updated. So this little software cache here helps with that. ZFP also supports compression for I/O. So you might imagine running a simulation using conventional floating points, but then you just want to write out the data in compressed form, and ZFP supports that using a number of different backends, for instance, OpenMP, CUDA, HIPID, and others as well. We also have an FPGA implementation of this. We support several different languages and so forth. So I guess I'm done with the marketing slides for ZFP, and we sort of need to move on and get back to what the topic of this paper really is. So, but first, I just want to show some results as sort of put things in context, and then we'll talk about what's new in this paper. One question is, since ZFP is based on a block decomposition. The question is, are there sort of these block artifacts or that most people are familiar with from JPEG image compression if you crank up the compression factor a little bit too high? So one case where this would show up is when you compute or estimate derivatives using finite differences. So what we've done here is generate a synthetic, very nonlinear field that we've also added a lot of noise to. And this field was designed so that when we compute the Laplacian, that is the sum of second derivatives, we end up with these perfectly concentric spheres as isocontours, and that's what's being shown here. You can also see these dark bands that are dependent on the normal to the isosurface, which is sensitive, which depends on the third derivative of the original field. So we're really stressing things here. What I'm showing here is what ZFP does with this. At 6 bits per value, you can see probably some minor artifacts, but this is a factor of 10 compression here. And you really want to compare this to a standard IEEE half precision representation, where you can see a huge amount of noise in this computed isocontour. Here using 16 bits per value instead of just 6, as ZFP uses. Posits do better in this case, but even when you look at IEEE single precision using 32 bits per value, ZFP actually does better in this particular case. So what's the reason for that? Well, what I'm showing here on the vertical axis is the L2 error in the finite difference estimation of a derivative as a function of grid spacing that's shown on the right here. So as we move from right to left, we get to finer and finer grids. So when you compute finite differences, there's also always a truncation error term that's dependent on essentially how wide your finite difference stencil is. So you get finer grids, the truncation error goes down. However, eventually round-off error kicks in. Here for double precision, you'll see that the actual error in the double precision finite difference estimate is essentially the sum of these two error terms. So if you compute it and plot it, you'll see that, just like so. With ZFP, you also have a compression error term that's essentially equivalent to round-off error. It's just due to truncating the ZFP representation, which essentially is the same thing as doing round-off. But so you have the original truncation error term, the compression error, and because ZFP returns double precision numbers in IEEE format, there's still the round-off error term. So if you compute the ZFP error, here shown in light blue, you'll see that it's just a sum of those three terms. But the interesting thing here is that the compression error actually decreases with finite grid spacing. And the reason for that is that the values become more and more correlated and similar as you go to a finer and finer grid. Of course, we can't do better in double precision because we're returning double precision numbers. But contrast this to 32-bit floating points. Here we're using 28-bit ZFP, and you'll see that there's something like 8 orders of magnitude difference in error between the two, even though ZFP uses less storage in this case. Here's a little simulation we ran with a helium bubble that gets impacted by a shock that arrives from the left here. We have double precision on top, ZFP using 16 bits of storage on the bottom here, and we've compared this with other 16-bit representations. So IEEE half precision and 16-bit posits, and you can see some fairly obvious artifacts here by using posits and IEEE, whereas with ZFP you can't really tell much of a difference. I said previously that you can use a fixed number of bits per block using ZFP, but you could also specify a tolerance, for instance, a fixed precision in terms of uncompressed number of bits. So in this case, we're using 40 uncompressed bits per block, and then the better the data compresses, the smaller it is. So each pixel here corresponds to a ZFP block that's been colored by the number of bits that we use to represent it. And I'll run the little animation here, and you can see how this progresses. By doing so, we don't waste a lot of bits on very easy to compress regions where you don't need more precision anyway, right? And in doing so, you can be more economical about where you spend your bits. So if you look at the actual error in the solution here as a function of time, what we've compared here is IEEE floating point, 32 bits, using, shown here in red, 32-bit posits, and then 32-bit fixed rate ZFP, where we use a fixed 32 bits per block. And we're comparing that against this new adaptive ZFP representation that uses 28 bits per block. And you can see there's a fairly dramatic improvement in error, even though ZFP in adaptive mode uses fewer bits, again, 28 bits per block in this case. Okay, so I've talked about why ZFP is a good format, so why do we need a new one? So this paper is really about looking into how can we generalize posits to multidimensional blocks. So there are some reasons for doing this. We've implemented ZFP on an FPGA, and the hardware implementation is actually kind of gnarly. There are lots of different special cases and so forth that you have to deal with, lots of different steps. So if you can cut down on this, you might end up with something that's a little bit more efficient. You know, posits are extremely elegant. It would be really nice to see how we can generalize this elegant representation from scalars to vectors, matrices, and tensors, and so forth. I think there are also some points of theoretical interest here. So I sat down and tried to figure out how this could be done. So I developed what I call multiposits, that are a tensor generalization of posits to multiple dimensions. The idea, as in ZFP, is to store blocks of n correlated scalars together. We're going to reuse some of the ZFP machinery, and particularly it's the correlating transform, to remove some redundancy. After applying that transform, we represent the coefficients at standard posits, and instead of just naively interleaving the bits of these posits, we're going to use the bisection-based framework that I discussed earlier to output the bits in an error-optimal order. Okay, so this works for posits, but it also works for other universal codes. So the key idea here is to essentially perform vector quantization by performing n axis-aligned cuts in this sort of n-dimensional space. Or, well, potentially more than n, but we have this n-dimensional cube that we live in that we want to perform axis line cuts in. Again, generalizing the bisection-based framework, we maintain one interval per coefficient, and we make sure that the vector x that we want to encode here is contained in this interval. So in each step, we partition one of the intervals, and we determine whether x is in the upper or the lower half, and we emit the bit that indicates that. And so in doing so, what we're doing is essentially just taking these coefficients, converting them to posits, and then interleaving in sort of the best possible order. So the algorithm for doing so is actually quite simple. I don't want to spend too much time on this, but the idea is that we apply our decorrelation step, that's just a matrix vector multiplication. We then reorder the coefficients based on their anticipated magnitude. This is a fixed permutation that's applied to them. And then we initialize our hyperrectangle in n-dimensional space that x lies in, and we're going to then narrow our down here. So really the most key step here is step 5 here, where we have to identify the widest dimension of this hyperrectangle. And then after that, we essentially just split along that dimension, put a 0-bit or a 1-bit, depending on where x is, and then we loop around. We might terminate this earlier if we've specified an error tolerance epsilon. Otherwise, we just keep going until we run out of precision. So p here represents the precision number of bits per value. So more graphically, the way this looks is that we're starting with this. So in this case, we want to encode a vector of length 2. So we have an x component, x equals 1.9, a y component that equals 0.1. And maybe, I don't know if you can see this, but there's a little dot here that indicates where this value actually lies. So we're going to encode this two-dimensional vector using the algorithm from the previous slide. And the resulting code word that we end up with is indicated by C here. What I've also shown is the actual posit representation of x and y using an exponent size of 1 in this particular case. So what we end up doing is, because the x and the y intervals in this case are both infinite, we just arbitrarily start with x. And what I'm going to do here is shade the region in which x, or the vector x, does not lie in. So we start by comparing against 0. In this case, x is positive. So we're going to shade the region less than 0 here. Then the y interval is widest, so we're going to perform the cut along y. Now the intervals are the same size, so we go back to x again. Posits will then compare against the number 1 in this case. So x is greater than 1. Then we compare again the y components. So in this case, we've only alternated between x and y. But now we see that y is actually contained between 0 and 1 in this case, whereas x is still unbounded. So we're going to refine x in this case, and now we have actually a fully bounded interval. But as you can see, it's actually wider than it's tall. So it makes more sense here to reduce the error by continuing the refinement along x, and that's also what the algorithm does here. So it keeps going and actually emits 3 bits from the x component in a row. And now it's taller, so we've got a y and so forth, and we keep going here until we narrow in on x, and we sort of pick x or y depending on the width and height of this this rectangle. So that's how we encode that. All right, so I'm going to talk briefly here about some results. So in order to compare this new multiposit representation with posits, IEEE, ZFP, and everything, we want to make sure that we use the same framework for doing so. So we're going to be using ZFP's tile multidimensional arrays. These arrays support a plugin codec that allows you to essentially specify which number format you want to store values in. You're still going to make use of ZFP's double precision cache, and all arithmetic here will be done also in double precision. So we're really only using the different representations to store things in memory. Again, we're going to compare a few different storage formats. And in our evaluation, we distinguish between what we call a fixed rate representation, where we allocate the same number of bits to all blocks, and a fixed accuracy mode indicated by -A on the following slides, where we essentially, as I showed earlier, we just terminate the encoding once we reach an absolute error tolerance. And that results, of course, in a variable number of bits per block that might not be suitable for random access, but for sequential access, for instance, if we were to just store this on disk, that would be just fine. So the first result here plots on the vertical axis what I call the accuracy gain, which essentially indicates the number of bits that a number format can infer, essentially a measure of compression. So higher is better here. You actually have the formula here. It involves the actual standard deviation of the data itself, the error in the data introduced by the number representation, as well as the rate measured in number of bits per value amortized. So we expect that as the rate increases by 1 bit, the error will go down by half, and as a result, this accuracy gain will essentially stay constant. And that's also what you're seeing in some of these plots here, that you reach sort of these plateaus where initially you might see some compression, but essentially eventually the bits just become random, and we just plateau out here. So the bottom curve here corresponds to IEEE single precision and half precision. You'll see that by using more exponent bits in single precision, you actually lose some accuracy by doing so. The next 2 curves that essentially overlap are just standard posits and standardized delta codes that are essentially identical in this case. The next one up here is a fixed rate representation of multiposits. So you're seeing we actually gained some accuracy, about 8 bits or so of accuracy by using multiposits in this case. We then go to ZFP in its fixed rate mode that achieves even a greater accuracy gain. And then we have two curves that corresponds to the fixed accuracy mode where we can be smarter about bit allocation. So for multiposits, you're seeing quite a significant increase here for ZFP, and even greater increase, and eventually the error goes to infinity here. So the accuracy gain also goes to infinity in that case, or the error goes to 0, so the accuracy gain goes to infinity. We're doing the same thing with a different field on the right here. You can see essentially the same kind of pattern between these different codes. In this case, we weren't able to losslessly compress this. There's sort of a finite round-off error that happens, so therefore, eventually the accuracy gains tapers off when you reset. What we're doing here is solving the Poisson equation. So a partial differential equation, and we're plotting here the error as a function of the number of iterations. And using half precision and posits, you see that you quickly converge to a constant error level. We essentially run out of precision. You can't do any better. With multiposits, using the same number of bits, 16, you do quite a bit better, by 3 orders of magnitude better. It's close to IEEE single precision. If you keep going further down, you'll see that ZFP, actually using only 16 bits, does even better than floats and posits in this case. And then multiposits at 32 bits do even better. Okay, so I only have a few more slides here. I'm going to wrap up. Multiposits have some issues. Rounding is a challenge, for instance, in that for these fixed rate representations, you don't know which bits of a given coefficient will actually be retained. So rounding becomes an issue. In order to bound intervals using multiposits, you need at least two n bits. Okay, so 2 bits per value to narrow it down to something finite. Sometimes you need even more bits, okay? And ZFP really avoids this by using a single common exponent. That's a much more efficient way of doing things. We also saw in the previous slide sort of these discontinuous jumps. If I can just go back quickly to this slide here, you see these discontinuous jumps in the multiposit representation. That's because every 2 to the ES bits, you get more regime bits for a bunch of coefficients at one, and typically those are all 0 bits anyway, so they don't improve the accuracy, but they impact the storage cost. So that's where you see those discontinuous jumps. Also, the correlating transform that we used in this case tends to shrink the values towards 0. That was needed to avoid overflow in the ZFP representation, but that means that the values actually move away from this golden zone near 1, right? They become smaller and smaller. You need more regime bits to represent them. What I'm showing here is that it's just this field that's being visualized using 6 bits per value, using these different representations. I've zoomed in on them, and you can see that with posits, you get a very sort of a pixelated, blocky look. Multiposits do better here at 6 bits per value. ZFP is essentially visually identical to IEEE float at 6 bits. When you go to 4 bits, the story is somewhat different though. Multiposits actually have an issue. And once again, this is due to this reduction in magnitude of the coefficient, so that they move away from the golden zone, and multiposits don't work well in that case. So we need to figure out ways to address that. All right, I'm on my last slide, so I just want to conclude this talk. So this new multiposit representation is sort of a generalization of posits from scalars to vectors, as well as to blocks of values from scalar fields that usually gives you 2 to 3 orders of magnitude improvement, especially at higher reasonable rates, say at between 16 and 32 bits of storage. It's a much simpler representation than ZFP. It's not really competitive in terms of accuracy, however. There are some issues. The way we implemented this, we're emitting 1 bit at a time. That's very inefficient. And we also have to perform this data-dependent sorting step that's costly. So if we actually knew the way that the coefficients were distributed ahead of time, or had at least a reasonable estimate on it, then we could predetermine the bit order and make this extremely fast, okay? We would just reuse sort of standard scalar posit encoding and then interleave the bits after that. I didn't really talk about this here, but we can also imagine using variable rate scalar posits that might be suitable, for instance, for doing I/O, where you're more clever about how many bits you use per posit, something that will be mentioned more in the paper. There's some future work that we'd like to look into. So we've only looked at generalizing posits, but the same framework accommodates other representations like alias codes, URR, and as well as others. We need to look into other decorrelating transforms, as I mentioned, particularly ones that are norm preserving. We might want to look at the discrete cosine transform and others as well. And finally, the coding scheme is kind of naive here. We essentially just one-to-one outputting bits verbatim, and you can actually do a better job compressing them because there's still a lot of redundancy in there that we haven't teased out already. So a future work might be looking at how we can be more clever about this. And that concludes my talk. I'm sorry I'm a little bit over time, but I think we still might have some time for questions, hopefully. Thank you.
Thank you very much, Peter. Yeah, you went over time, but you were invited to do so, and I'm glad you did because you had a lot to cover. Very interesting, and thank you for an excellent talk. We don't seem to have any questions on Pigeonhole. I did think of a couple of questions or comments. Very early on, you showed the bit planes of 16-bit posits. And
yes.
The first three of them look like a Holstein cow kind of thing. And then I noticed the next one looks like it was the negative, where the black became white, the white became black. And I wondered if that's the last bit of the regime flipping.
That's correct.
Okay, that's what I thought was happening.
So in this particular case, the values were all below 0. So we start with a bunch of 0 bits, right? And then yes, that's a regime.
I don't know if there's any compressibility help there, but you'll always see in a posit, you know, that the bit plane will be the flip of the previous one because of that. And
yep.
Just indicate when that happens. I was amazed that there was a number like 4/15 to the D power in your multiposits encoding algorithm. Where do such constants come from? 4/15?
That comes from the particular transform that we borrowed from ZFP. Okay. If it was perfectly orthogonal, then that constant would be 1/4. It's slightly non-orthogonal, and it essentially has that condition number. So when we apply that transform in D dimensions, or when we perform the inverse transform, we might actually expand coefficients by that much. And that's the reason for why we have to multiply that to conservatively stay within the error tolerance. But that was sort of a conscious decision we made because it makes the transform a lot easier to implement. You don't need any divisions or scalings by weird constants this way.
Yeah. Well, ever since you've been comparing ZFP with posits, I thought that's not fair because they're orthogonal concepts. So I'm really glad you finally tried to apply the ZFP compression techniques to posits the way you've been applying them to floats. But I think we can see pretty conclusively that floats are better adapted to ZFP than posits are. That whole idea, you really need a kind of a flat accuracy in order for it to work neatly and well. You don't, and posits don't do that because they have this golden zone. Would that be a fair way of summarizing it?
Yeah, I think in retrospect, after I did this work and got the results, I kind of realized that, yeah, there are some obvious drawbacks here and some things that we can do better for this to work better with posits, like staying within the golden zone, right? That becomes fairly important.
And knowing the way your mind works, you will still continue to work on this and eventually come up with a breakthrough that maybe makes it takes advantage of the posit concentration of accuracy in the center, and also still compresses extremely well.
Yes, so. Yeah. Keep in mind that this is really only the first step in this direction, right? I actually view this paper somewhat as sort of a negative result. In that I was hoping that we'd get a lot closer to ZFP, and we don't, and there are also even some issues when comparing with standard posits in some extreme cases, right? So I think there's
negative results are welcome in science. This is not a marketing exercise, right?
Right. Well, yeah. So you know, hopefully others will improve on this in the future. But I thought it was an interesting enough idea to sort of get.
It is absolutely fascinating, and those slides are spectacular. 86 megabytes worth of slides there, folks.
Thanks, John.
Anyway, thanks again. Our next speaker is Syed Hamid Fatemi Langroudi, and he goes by Hamid. He's a PhD student at Neuromorphic AI Lab, led by Dr. Risha Kudutipudi. And he is also a student member of IEEE Computer Science Society and IEEE Study Group on the numerical format for machine learning. His current research interests include deep learning and computer arithmetic. His primary research area is developing a new computer arithmetic algorithm for energy efficient deep neural networks. And he's going to talk to us about something called ACTION, Automated Hardware Software Co-Design Framework for Low Precision Numerical Format Selection in TinyML. That's something that needs an acronym if ever there was one. Go ahead, Hamed. You're muted. Take your mute off, Hamed.
Yeah.
There you go.
So, hello everyone. So I would like to thank John for nice introduction, and I'm honored to be here to talk our recent work, which we're trying to find a way to select the numerical formats based on designing automated hardware software co-design. So this is a joint work with some of my colleagues in UTSA, Vedant, Becky, and Tej, and most of the hardware design is done by Vedant and the joint work with my advisor, Dr. Kutitipudi. So I have to click here and then. Okay. So if you look at this plot, we have a couple of challenges in deploying DNN model on the edge. So one of the challenge is model size. The model size of different deep neural network is growing rapidly. For example, one of the neural network is transformer is growing 240 times in 2 years. So, but at the same time, the memory offered by AI accelerator is just growing by 2x. So you can see that there is a large gap between what the memory footprint is offered by AI accelerator and what is the parameter of deep neural network. So this is also happening, these trends for computing. For example, for training neural networks, the number of the computation is rapidly growing. For example, for transformer, the number of the computation growing for training neural network to 50 times. And also, even for computer vision models, which is use less computation than the transformer, so growing is 50 times. And we are scaling based on the Moore law, and the growing of the AI accelerator in terms of the computation is 2x. So again, there is a gap between the number of computation needed for different neural networks and what is offered by current accelerator is high. And at the same time, tangible to this complexity we have for deep neural networks, we have lots of edge devices exist today, and there is, and deep neural network has been successful for different applications. And these two motivate us to use intelligence on the edge devices. And the technology and research studying this putting the intelligence on the edge is called TinyML, and TinyML trying to enable on-device sensor data analytics at extremely low power, typically in less than milliwatts of power consumption. So this case solving this problem, trying to put intelligence at the edge is much high, become harder than putting the intelligence in the data center and so on. For example, you want to have the intelligence on the power consumption less than milliwatts, area constraint less than 20 millimeters of a square, or the memory constraint is like 100 kilowatt, and also you have a latency constraint, about 10 nanosecond to 100 nanosecond. So this is very difficult challenge, and several research doing on this problem. So one of the solution to route the TinyML and reduce the complexity of neural network is model compression. So we want to compress our models, deep neural network models, with different techniques exist today. For example, you can use pruning, low ranks decomposition, and also you can use distillation and so on. But one of the technique is low precision arithmetic, which is you try to reduce the number of bit precision, and and the gain is reduction in memory footprint, reduction in latency, or reduction in energy consumption. So, for example, you can use 32-bit floating point. Instead of using 32 floating point, you can use 8-bit floating point, and you gain memory footprint and so on. But there is a side effect here. So when you reducing the bit precision, the quantization error is increased. For example, if you reduce floating point 32 bits to like fixed point 8 bits, you can see the degradation of the accuracy, like 5% degradation. So, the real question is, which low precision numerical format can meet the dual objective? You want to a numerical format which shows the high inference or training accuracy, and at the same time, minimal hardware resources. So, for example, if you bring to binary, so the resources is reduced a lot, but at the same time, the accuracy is degraded. So you want to have some numerical format in trade-off between the accuracy and hardware resources. So the several research shows different numerical format, the benefit of different numerical formats, and a lot of research have done. But there is also another challenge, which is trying to identify the optimal numerical format for a DNN accelerator. So this is the real challenge, because there is an incompatibility in accuracy and hardware complexity trade-off offered by various numerical formats. Some of the numerical format optimize for the accuracy, some of them optimize for the power consumption. So that, because the numerical format has different characteristic, so there exists large, the size of the search space is large. So large design search space exists for numerical format and bit precision acceleration. So for example, in this figure, if we have a ResNet 50 layer, ResNet 50, and we have 4 options for the precision. We have the search space of 3 multiplied 4 power 50, which is very huge search space. And even we will not use the mixed precision. The search space is around the hundreds or 1,000, which you can use. You can do manually. You need tools for this problem. At the same time, the hardware constraint also changing from the one edge devices to another edge devices. For example, the constraint we have for the A12 is different the constraint we have for ARM M7. So the low precision framework should have the capability of the changing the constraint in a runtime. So that is the solution for we propose as an action framework, which is automated framework to identify the low precision numerical format. But before I delve into how that framework works, I just bring some explaining the numerical format in a summary we use for this study. We use 5 numerical formats: float, fixed point, posit, general posit, and tapered fixed point. But I will not explain the fixed point and floating point. I just explain other numerical format. And Posit, as we know, one of the innovation, the regime encoding, which give us the tapered accuracy. In the small value, you have a more bit precision, and very large and very small, you have a less fraction. And how you just compute the regime value, just count all of the 0 and 1 up to you reach to termination value. For example, here, based on you start with the 0, you just count all of the 0, and then the value is -5. And there is a couple of benefits over float, like higher decimal accuracy, and also if you use the quire, the program reproducibility is increased. And you can see if some example here, n equal 16 and es equal 2. And so if the bit precision, for example, in the format, if the fraction is out, just padded with the 0. And in the example, for example, here, the regime value is 1, 1, 0. You just started with 1, and you just count, is become 2 and -1, and you have a value. So in 2018, we just tried see different distribution of weight in the neural network, and also plotting the distribution of the posit with different scaling and so on. And we find that the posit has very similarity distribution with the distribution of the weights in neural networks. And because of that, the quantization error is decreased significantly, and we can use posit for neural networks. And that was our start point to using or have a framework with the posit numerical format. And more details of these studies, all of the studies we have done, you can see in the Medium article we have published recently. But in neural network, each layer have different distribution. The tapered precision is different. So it will benefit for us if you have a numerical format when you can adjust the tapering. And that is offered by general posit with just one parameter, which is called RS, which is the maximum number of bits allocated for regime. You can control or adjusting the tapering. For example, for posit, standard posit, you have a RS maximum, and you have the maximum steply tapered accuracy. And if you go to another extreme, so you have very similar to float. So you have a flat and very similar to float. So you have a flexibility between posit, float, and a couple of other tapered precision. So, and with another parameter, which is called exponent bias, you can change the golden zone. So that might be even helpful for multi-posit dimension. So you can change the golden zone in order to your distribution in that golden zone. So, and this example, not the same bit precision, and if we have a RS2 and the exponent bias as a -2, so here again is 1, 1, and the termination is hidden as a 0, and we just calculate as the same, and the value just decrease. So the same concept we can use for fixed point, which is the somehow is we call taper fixed point or taper. John call also. It's imagine the fixed point. You have an integer and fraction. So the integer part you can use regime encoding, and the fraction is the same as the fixed point. So the benefit over the fixed one, you have a variable dynamic range, variable taper precision, and again you have maximum taper to flats, similar to the fixed point. And but just one trick you have to use to don't have a redundant number. So you have the sign have and almost this happened in the fixed one also. The sign has two roles, and you just if not the sign, so you convert it here as like if 0 is 1 and 1 as a 0, and then use these bits for the integer part as the first bit of the regime encoding. For example, here the value is 1, 1, and 0, which is 3, and then -1 become 2. And because of is like similar to fixed point, we didn't scale and just added to the fraction. And the scaling just happened with the scaling factor, and you have a very small range. And these are all summary of the numerical format, plus the float and fixed point we have used in the framework. And if we compare different numerical format based on the decimal accuracy, we can see that the Posit and general Posit have a tapered decimal accuracy. And the general Posit is between Posit and float. Started with the tapered accuracy, and then is a flat. And also, but the fixed point is started from the tapering from the maximum magnitude value to the minimum magnitude value as a long ramp shape. So this is different than what we want for neural network. Is the distribution of the neural network is more close to Posit and general Posit. So these are the summary of the numerical format. Let me explain how the action framework works. So the key idea is here, we use the integer linear programming to identify the optimal numerical format and some of the subspace in the accelerator design based on what the user wants. So user can, as the cartoon showing here, is user can select the constraint. For example, here some constraint on EDP, and also some constraint on the EDP, and some constraint on the accuracy. And you user select the models also, and this is the input to the action framework. The initialization is just make sure you have a weight in the floating point 32, and then you want to convert. And after that, you use the ILP optimization, and we evaluate each of these action of the numerical format and architecture with evaluation of the accuracy and hardware complexity. And the framework support 5 numerical format, 3 data flow approach, and different configuration of the processing element, and is evaluated for different metrics like energy, power, 8 different metrics. So if we look at it as an example of how the evaluator is work, for example, here at the right, we have an example for the general Posit numerical format for 5 to 8-bit. And for each of the layers, we try to the distribution similar to the distribution of the parameters, and based on that, we select the RS and SC. And then the important point here is we, for example, if the convolution operation here for this layer, we perform in the general Posit. It's not like just quantize to general Posit and then convert it to floating point and then dequantize. We do all operation that general Posit. And we use the IFP optimization. You can minimize or maximize the objective respect to different subjects. For example, you can maximize the accuracy respect to the EDP constraint or power constraint. And in the hardware side, we simulate 5 different P array configuration, and all of the MAC operation we use is synthesized in 32 nanometers. So in the hardware, what we have done is just synthesize the MAC operation, and we use a SCALE-SIM, which is just an ARM software to simulate the Iris version 2 as a template of the AI accelerator, and we get the result from that frameworks. We evaluated different numerical format and action framework in 3 different data sets and applications. The reason we select these data sets is part of TinyML version 0.5 benchmark, and we did this for TinyML. And so different models, for example, different data sets. One of them about the speech, Cipher 10 is image classification, and visual wakeboard is just images, which is a person in image or not. And different neural network from ResNet 8, deepwise convolution, mobile regression 1. And the result is very interesting. We have seen that general Posit for all of the experiments outperform all other numerical formats. So if the accuracy is or target, definitely is general Posit is our choice. And after the general Posit, the Posit shows better result, and the tapered fixed points also showing very interesting result, and some very similar to the result to floating points actually. And even for example, for image classification is very close to very close to floating point 32. And but many cases we have a trade-off. We want to have a accuracy, energy delay product trade-off, and so on. And this example showing how the action framework work for and user can define the constraint. For example, If you want to maximize accuracy respect to the constraint in the EDP and accuracy also, essentially you have this highlighted box. And in this highlighted box, you say, for example, the accuracy should be bigger than 70% and the EDP bigger than less than 7.44. So in that box, you want to find the maximum accuracy. So in that case, the general posit with 8-bit and 0 exponent has maximum accuracy. If you do for other benchmark like keyboard spotting, the general posit H0 showing a better result. And for the memory, if we do for memory, the general posit is 7-bit has a maximum accuracy. For example, for frequency, we want to have a maximum frequency in the range, in the constraint, for example, the accuracy more than 70%, and we want to find the maximum frequency rather than the accuracy. So in that case, the K-perfect one shows a better result. So these are just example, and the user can define the constraint and have the numerical format answer. So to conclude, we develop a low precision hardware software co-design framework to choose the right numerical format. And this is very useful for earliest stage design exploration for designing the accelerator and based on user-defined constraint. And we demonstrate different numerical format and different platform. And what we found, especially for this benchmark, we find that general posit has 25% better result of other numerical format. And what other important things is, if we consider the trade-off, we have seen the general posit and K-perfect point outperform other numerical format. And the ILP is very fast. We can get the result in less than a second, actually. And but the reinforcement learning is very slow. So I would like to acknowledge Dr. Chung Gustafson for several discussions we have for a long time from in 2018 about different projects in the Posit, and I would like to thank all of the new AI lab member and UTSA member help us, and also the Matrix center, which is support this work. Thank you.
Thank you very much. Thank you very much, Hamid. What an amazing talk. I'm so glad you named the 8 figures of merit you're going to study. So I wish more papers would do that. They compare a number format with a number format, but they don't set out initially, here's what we consider to be a good thing to have. So I really appreciate that you did that. It's a lot of fun for me to just throw a number format out there, and then a year later or so, a paper like this comes out and shows exactly what it could do. It's like having a very extended group of grad students worldwide working on these ideas. But the merits of generalized posits for this, the accuracy difference was just spectacular. I didn't expect it to be that good. It really looks like there is an underlying perfect distribution that we're getting close to. And one of the things I wanted to ask you if you ever tried is having a different RS value for positive exponents and negative exponents.
Right, I haven't tried. I plan to do that, but I haven't tried that.
We tried it at NUS and it worked. It got us a better result than if we didn't do it. We also did neural network studies with generalized posits, though not nearly as extensive as what you've done here. But you don't necessarily want an even distribution from very large to very small numbers with neural networks, because you don't need the large ones. And so you can set a kind of you can blunt off, make it look more like a floating point for positive exponents, but make it look more like a posit for negative exponents. And then you get all the accuracy, constant accuracy for the accumulations. As you accumulate larger numbers, then you don't lose any of the accuracy, and that's sometimes critical to the classification. And so there may be even a little bit more tuning that can be done, that can be tweaking. I'd also like to comment that the IEEE committee formed a subcommittee to study standardization of a number format for machine learning. And I sit on that, and I think some of the members of your team do as well, and I hope we continue to, because it's studies like yours that show it is way too early to standardize on any kind of number representation. We keep finding all these improvements, and if you try to lock something in and carve it in stone as this is the number format and standardize it, it could turn out to be really a wrong choice in just 6 months from now. So I sit on the committee not to advance their cause, but to prevent it from making really a decision.
Yeah, that's a study shows there is no launch theorem for all of the numerical format. It's very dependent on the application right now, and very dependent on the constraint we have. So maybe and many cases, if maybe in the future we find a numerical format works for all, but for currents, that's why we came up with this framework that give you, based on the application and based on the constraint, give you the numerical format at the right point.
Yeah, there's going to be a talk after the lunch break by the people from National University of Singapore, who've been also doing all these variations on how can we trim down the number of bits, studying using some of the same benchmarks. So I hope you're in the audience for that one, Hamed.
Yeah.
Okay, well, we are done 15 minutes. Actually, we're on the schedule we originally promised to be done at 15 minutes after the hour. So we will break now for lunch, and slightly with a 15-minute margin, and we will return at, I guess, an hour and 45 minutes from now. See you all back then. Thank you.
Yeah.